So welcome back, everybody. This is day 4. So we're almost done. Like it seems like we've barely scratched the surface in a way, right? You'll probably have a lot more questions than answers, or you'll have more questions by the end of the week than you had in the beginning of the week. But that's kind of, well, that's to be expected. So the plan is this: today we're going to step through this, what's called a Jupyter notebook, and the notebook is a bunch of code in Python that will make some really pretty psychedelic graphics. And I'm going to show you how to use it and talk about some ideas for things you can do with it. And later I'll show you like a showcase of some work that I've done with this technique, so to try to get you kind of excited about it. And also, so that will be kind of like the main course for today. I think we'll see how long it takes, we'll see how much time we want to give to everyone to kind of work with it, but you'll have it moving forward. And then I was thinking about how to approach the last, like tomorrow basically, and maybe the second half of today. And I think the best thing, just like having kind of studied the way people reacted the last 3 days, what I want to do is I want to show you a bunch of more advanced methods for making generative art. However, because of the size of the course, I'm afraid to do it in such a way that you guys are following along at the same time, because I'm going to use an online cloud computation service called Paperspace, and I think that if we all were to use it at the same time, it would probably mean that none of us are using it at the same time. Because I've done it with like 25 people before, and that was actually hard. And actually, I also think it's better not to do it that way, because not to do it with you following along, because I think we'll be able to get through more things. I'll be able to kind of just show you the entire process, and because I'll be using an online cloud computer, it'll be such that I'm going to take you through every single step of the process, and it's being recorded. So you're going to have a tutorial that will be available online for all of you after the class, that you'll be able to just watch and repeat all the steps to get exactly, to have exactly what you need. So it doesn't make sense to necessarily, like, I think it's a more effective use of time. We'll be able to look through more things if we just do it that way. I think that's going to be the best strategy. So that will be basically tomorrow. And so there's 3 things I'm going to do. So the first thing is this notebook. The second thing is I want to do a quick lecture about generative models and pix-to-pix and all of this kind of stuff that we're going to look at in more depth tomorrow. And then tomorrow will be the tutorial. So that's kind of what's there to look forward to. Okay, so let's do this, yeah? So everyone's got this link, right? So basically, when you open this page, you should see something like this: neural synthesis, feature visualization, and Deepdream notes. And you should have, it'll either say, so if you have to log in, make sure you're logged into Google if you want to run through it, if you actually want to execute it. And then it should be something like in the top left corner, it'll say open in playground. So if you don't see that, that means you're already in it. Either that, or you'll see a connect button at the top right. So just click once you see that, you should be able to click the connect button, and it'll go allocating, connecting, and then at some point in a few seconds, hopefully, you should see initializing connected. So basically everyone should see something like this. Yeah, and I'm going to make this a little bigger for you. I'm also going to, the table of contents is empty, so I'm just going to exit out of that, so we just have the notebook. So is that good for everyone? Everyone's been able to connect? Raise your hand if you see a green check mark and connected. Okay, not so bad. Anybody having, is it like stuck on allocating or something like that? Okay, so yeah, just if you, so again, like this is optional, of course. Like if you don't have a Google account, don't feel pressured to like get one, because they will surveil you. So that's, I can't recommend getting one. In fact, I recommend not getting one if you don't already have one. That's actually like a great idea. Yeah. I'm sorry, Google, if you're watching this, like, because they are, because this is going online later, probably on YouTube or something else that Google owns. Anyway, I'm sorry. What was your question? Yeah. If you're offline, then that means you must have no Wi-Fi right now. So check if you're on the internet. It still works? Okay. Okay, so don't worry about that. Yeah, I'm not sure what that's supposed to signify. So basically we introduced this yesterday. We talked about this idea of feature visualization, so that the notes at the top here, you'll see that they just just summarize what we introduced yesterday in the lecture. So I talked about the idea of feature visualization, something that scientists have been doing in the machine learning community for about 6, 7, 8 years or so, and then Deepdream in 2015, and then basically this notebook that we're looking at is so it starts as a copy of the official Deepdream notebook of the TensorFlow repository. So if you find the main GitHub repository for TensorFlow, I'm basically just recapping that. The first half of this notebook is basically just a copy of that, more or less. It's been embedded into a Colab instance here, and it will take us through the process. And then later, I'll be showing you some techniques that I added to it, basically to make the video that I showed you yesterday, very briefly at the end before we left. So now just a few notes about Colab and Jupyter Notebook. So Jupyter Notebook is a relatively new, last couple of years, this application that allows you to embed code and notes into a single file that you can browse, that you can look at inside of a browser, and it's connected to some computer, like a server that executes the code. And that server is most frequently the same computer as the one that you're running inside the browser in, but it doesn't have to be. So a Jupyter Notebook can be communicating remotely with some other computer somewhere. And that's actually the nice thing about Colab. Colab is or Collaboratory is also a new service from Google. I think it's just maybe 6 months old or something like that. And it basically runs a Jupyter Notebook, or a fork of Jupyter Notebook, on Google's own servers. So when we execute the code here, it's actually sending the code to Google. Google is executing it on their own computers somewhere, and then sending us back the results. So the reason why we have to do this is because this will not easily run on a laptop, because it has to do like several hundred million calculations per second and requires a lot of memory. So unless some of you may have computers that are capable of this, like a few people mentioned they have sort of gamer laptops, those will probably work, so you could download this, but for the most part it's easiest to run it off of cloud compute. So now one thing about Colab though is that first of all it doesn't run that fast. So Google makes it run at something like half speed or 1/3 speed that you would normally expect if you had that same hardware, and that's because they don't want people to abuse it. So it's a bit rate limited, but it's pretty fast, so it's not so bad. And also the storage while you're connected to a notebook, the storage is temporary. So as soon as you exit the notebook, all of the storage is flushed out; it's gone. So you can't, so like basically whatever you create, you have to make sure to save it with you before you leave the notebook. So that's just something to worry about. Later when of course, like if you really get into this technique, you can easily set it up on some cloud computer that you have permanent storage for. So that's going to be something I'll show you how to do tomorrow. So basically to execute these, so you'll see that basically as we scroll down, there's a whole bunch of these cells, and the cells have like a play button, and the play button will run that code. And then sometimes the cells are just notes, so all of these are either markdown cells, which have notes that you can read through, and I'll be kind of summarizing them, or code cells which have the play buttons that you can hit play on. So the first thing I want you to do, if you haven't already done it, is the first cell here where it says grab Inception model from online and unzip it. Please hit the play button and watch it do its thing. If you get a message where it says like do you want to write over this or something like that, like you already have it, do you want to write over it, that means you've done it twice, and then you could just cancel that. So you'll already have it. You should basically see something like this, and it should go pretty quickly. Now what it's doing is it's downloading the Inception model. The Inception is a neural network architecture that was trained by Google on many millions of images from ImageNet, and those images are just everything that you would expect to find in the internet. Cats mostly. Actually dogs mostly. So ImageNet is full of dogs. So like 200 breeds of dogs that are classified for whatever reason. And it's been trained, it's a really large network, and it's been trained on these many different categories of images. And so it's learned a whole bunch of features, right? That correspond to those kinds of images. And we're downloading it, and we're going to use it for this process. And anyone having any trouble? This worked for most people, right? Okay, so I'm going to continue. So basically, in the next cell, so where it says from future import print function, all this stuff, which ends in import TensorFlow as TF, just hit the play button on this, and you should see no output. Because basically all it's doing is it's importing all of the libraries that we're going to be using. So it should just kind of spin the wheel for a little while and then stop. And if you don't see any errors, that means that everything's good. We have all these libraries. This is, it's a good question. It doesn't tell us. You should be able to run it on either Python 2 or 3, I think. It is 3, probably. Yeah, that's probably the case. I think it's Python 3, but I'm not 100% sure. You can always check the version, but it doesn't should be fine either way. I'm sorry? I think you could do it either way in 2, but you can check later. It doesn't matter for us. So basically, the next cell is so run the next cell. Okay. So and I'm going to tell you what this cell does. So this cell, if you look at the code, it's not going to look particularly readable to you. It's a lot of TensorFlow magic, and what it's doing is it's basically loading the model, the Inception graph, and it's placing it into and it's basically allocating one of these, what's called in TensorFlow parlance, a computational graph. So it's creating an architecture for running this neural network on GPU, which is being allocated onto some GPU somewhere in some data center owned by Google for each of us at the same time, which is really lovely. And basically, we don't have to worry. These are a bunch of, basically, we're declaring a whole bunch of Python helper functions. Even if you do know Python, a lot of these won't make a lot of sense to you. We'll kind of talk about them as we need to, as we go through them. But for now, like what this is doing, you should see at the end here, it goes number of layers 59, total number of feature layers 7548. So what that means is that the Inception network has 59 layers. So it's a large neural network with 59 layers, and it has 7,548 separate feature channels. So remember yesterday when I was talking about how you can try to visualize what every single neuron in the network is capable of learning by doing these visualization experiments. So in the Inception network, there are 7,548 of them. So we have a lot of choices. We have a lot of options to investigate. And they go in a sequence of layers. There are 59 of them. So in the in the next cell, you'll see that if you run this, it's just going to spit out this output. So you'll see that what it does is it takes each of the layers and it prints them out for us. It prints out their name and the number of channels they have. So the very first few layers are called conv2d 0, pre-relu 64. So that means there are 64 channels in this layer. There are 64 channels in this layer. 192 channels in this layer, and so on. I use the word channel and neuron interchangeably, so they're kind of the same thing. So like each of these are, you can think of them all as feature detectors, right? So they're all detecting a certain kind of feature. And these layers are going in order from the beginning to the end of the network. And they have very obscure names. You don't have to worry too much about them, but basically, like you can see there, it goes from mixed 3A to mixed 4, mixed 5, and so it's kind of going in this sequence. And the ones in the early part of the network are the early layers. And as we mentioned with convolutional networks, they start by detecting very simple features, and then as you move through the network and go layer by layer, they start to detect progressively more and more complicated features, right? So the middle layers are detecting features of mid-complexity, and the later layers are detecting features of the most complexity, with the final layer being classification layer, right? So basically here, we're just printing out their names, and you're going to kind of use this as a reference because we're going to be referring to their names later. And just make sure you can note that the number next to it is the number of channels in that layer, and it adds up to roughly 7,500 of them. So the next cell is going to define the very first method that we'll use to render an image, and it's called render naive. So I just want you to run that. So make sure it circles around, and you won't see any output because it's just declaring the definition of the function and its code. Now this is like if you look at the code, it's of course very obscure. It's like a bunch of TensorFlow code. We're not going to look very deeply into how the TensorFlow code works because it's a little bit beyond the scope of this course. Once you do learn TensorFlow, most of it should make relative sense to you. I am going to kind of like briefly describe what it's doing at a high level, but we won't really look at the code. You can treat the code more or less like a black box for now. But let me kind of take you line by line, just tell you a little bit about what each line is doing, right? So what happens in render naive, because we're going to be using it in Excel. Actually, maybe it makes sense to just try to do a render naive first, and then I'll go back and tell you what the code is doing, so you can see what it does. So if you run the next cell that starts with image 0, right? What it's going to do is it's going to visualize, and by visualize I mean it's going to synthesize an image which maximally activates a particular channel of a particular layer in this network. And for example, I've chosen this layer, mixed 4D, 5x, 5x. You can see it's one of the layers from here. And channel number 20, right? So if we look for this mixed 4D, 5x, 5, so that's over here. And it has 32 channels. So make sure you don't use a channel number that's bigger than the number of channels that it has. And remember there's 0 index, so the last one is actually 31, right? So this will call the render naive function, and it will return us back an image, and then we just draw the image. We display the image here, and this is what it looks like. It doesn't look terribly exciting, right? It looks like mostly just high frequency noise. If you change this number, let's say like we make it 12, it'll do this to another one of the channels. Right? Now it doesn't look incredibly different, but if you look at it closely, you'll see that the features look slightly different. Now, what is actually going on here? So what the render naive function is doing, and the reason why it's called naive is that it does the simplest possible approach to synthesis. Basically, it does what was done in the very first example of this that I showed you by Simonian et al. Basically, like generating the ostriches and the keyboards and Dalmatians and so on. It just tries to find a set of pixels which maximally activates that channel. And in the code, what it does basically is it defines the objective, which is in this TF reduce mean. So basically, trying to reduce the distance between the activations that this image will have and the activations we want. And the activations that we want are basically 0 for everything and 100% for that particular channel that we've selected. And render naive takes as its input an image. So you start with an image, right? And you can give it any image you want. You could give it an image of just random noise, which is what we're doing here. So this is the image being initialized. We're just making an image of random noise and then passing it to render naive over here. So if you give it an image of a photograph, it'll start with that, right? So that's something that we'll actually try to do later. And then it takes in 2 arguments, the number of iterations and the step size. And the step size is like, you can think of it as for each time it calculates, well, okay, wait, before I confuse you, let's go through each line of the code. So in this line of the code, it will give us a gradient, right? Or this actually just creates well, it's complicated. Like this function defines the gradient. And the gradient in this context means, and I'm gonna be using the word gradient a lot, so this is important to understand. In this context, the gradient is going to be a structure which is like the size of the image. It's going to be, you can almost think of it as like another image. It's a structure that is the size of the image, which contains the difference that we want to add to all of the pixels. So it's like the image that we're adding to the image that we have, the image that we're going to add on top of image 0. And it's just the differences in all the pixels that we want to add to it. And that comes from that comes from this statement over here. And then what it does is it basically runs it and gives it to us in this variable called g. And then it just does some normalization to it, and then it adds g to the image. And it does this many times, right? This is a loop. So it does this 20 times, for example. Calculates the gradient, and then adds the gradient to the image. Calculates the gradient, adds the gradient to the image. So if you do it for longer, right, like let's say we did this for 150, it'll take longer, but it should kind of double down in those features. And at some point it kind of stops learning, or it stops updating very much, so it's not really necessarily worth having this go very high. But basically, you can see that it's a little bit more pronounced now. Now, it doesn't look very good though, right? So it's nothing to brag about, right? And it turns out we can do a little bit better. And the next cell here will basically take the render naive thing and make it a little bit more complicated. And so let's define this. Let's actually run through this. It's called RenderMultiscale. Now, at this point, I'm not going to run through each line of the code because by now it's becoming like probably too confusing for the scope of this class. But I'll tell you the difference between this and the previous one. In RenderMultiscale, what it does is it actually tries to do this process at multiple scales, multiple sizes of the image. And what I mean by that is each of these, like when you try to activate one of these particular neurons, the feature detectors, they operate on a fixed scale, several pixels, right? Let's say 5 by 5 pixels in the first layer, and then later it's a little bit bigger, but it's always some fixed size. So that's kind of undesirable. Like maybe we want to be able to find that feature on multiple different sizes. And so the way this works is that it starts by taking the image that you give it at some size, like let's say it's like this big, and it does this process that I just described, the naive process, where it adds the gradient to it, and then what it actually does is it resizes the image. It makes it bigger by some ratio, and then it does the process again, and then it resizes it again and does the process again. And each time it resizes it, the image gets bigger, and so it will actually take longer to do the process because there's more pixels to calculate it over. But the thing is, because you're resizing the image from the original size, the features get preserved in like what was originally kind of a low resolution version of it. You're like expanding it, you're making it bigger. And so that has the effect of visualizing, that has the effect of bringing out those features at multiple sizes. So if that doesn't make too much sense, don't worry about it. The point is it will look a little bit better. So let's define this and let's run through an example. So here, now there's a few arguments that we have to begin to keep track of. So HW is the height width of the initial image, right? So we'll start with a canvas that's 200 by 200, and then this octave n is the number of times we want to resize it, right? So it'll be the number of scales upon which we want to visualize the features, or to activate the features. And then octave scale is that ratio, the resize ratio. So the bigger these numbers are, the bigger the final image will be, because it starts at 200, 200, and then 3 times it will resize it by a ratio of 1.3. So it'll basically end up being this much, 1.4 times 1.4 times 1.4. Actually, well, 3 octaves means it gets resized twice, so it's going to be 392. So basically, this will start by making a random image, and then we again pick a layer and the channel, and then we'll run the RenderMultiscale, and it will create this image, and then we'll display it. So let's actually make it take a little bit longer. I'm going to make it iter n 100. And if you want to try to change this number so everyone gets a different number, like, and even, you know, feel free to actually try a different feature as well. So like, maybe I'll do like mixed, this one instead. I'm going to pick mixed 3B, pre-relu, and there's 192 of them, so we can go up to that high. So I'm going to switch this to that, and let's do 190. So if I run this now, it's going to take a while now because it's doing 100 iterations at each scale. So the first octave is going to go by relatively quickly, but then it's going to take longer because at each octave we're making it bigger. So this might actually, well, yeah, this will actually, 100 iterations is probably too many. This will take like a minute. While it's doing that, I'm going to, we'll actually end up skipping the last one. Yeah, this is actually a little bit too long. Let me actually, so you can always, oh, that wasn't too bad, okay. So, okay, 100 iterations at 3 octaves. So you see that this feature looks like this, right? And it looks a little bit more interesting now than the last one, right? I'm going to actually like open this image in a new tab. If you ever want to save these, it's easy enough to just open them in a new tab. And that's what it looks like. If we do this, let's say, just move this by 1. I'll make it 189. So now I'm going to visualize a different feature. So let's see how this one ends up looking. Right, so this is just one, and they're basically, there's no order to them. So 190 and 189 are going to be as different from each other as 190 and 1. And they're going to be as different from each other as 2 neurons in different layers.
Can you tell from this information where you are in terms of layers, what you input or output?
This goes in order. So like the very first one's conv2D, that's like basically the first layer of convolution. So look at this one, right? Now I open this, it's completely different. Right. Okay, so that's the RenderMultiscale. Skip the next cell because this actually doesn't work. This just shows, because we don't actually have this image, we'd have to download it. This shows if you can get an image onto the Google storage, you can start with an actual image, you know, instead of actually, instead of starting with an image of random noise, you can, you know, hallucinate these features on top of an actual image. That's the whole Deepdream thing, right? So in Deepdream, you kind of start with a real image and then modify that image. We'll try to do that later, but I want to kind of continue with building up the main function. Now the last function is kind of this, or it's not the last one, but the last innovation, which is called RenderLaplaceNorm, basically takes this multi-scale approach, and it also uses what's called Laplacian normalization. So we're not gonna talk about Laplacian normalization in any detail because it's again also beyond the scope of this class, but it's a technique from computer vision, which is used to it's used for a lot of things, but for our case, the thing that it's used for is, if you look at these, they kind of have this one unfortunate aspect of them, which is that they seem like you see a lot of like very high saturation noise. Like it's very, very like you see there's a it's like very high frequency color, right? You got like neon pinks and neon yellows, and there's like just a lot of high frequencies in there. And so the Laplacian normalization actually, the multiscale generation actually helps with this, but the Laplacian normalization helps it even better. So if that doesn't make any sense, again, don't worry about it. We're gonna just declare this and run it, and you'll see that the results get slightly better. So I'm gonna run this, and then the next cell will do an example of this. And let's actually, I'm gonna make this a little smaller. Start 200 by 200, and let's say 3 octaves. Let's make the octave 1.3. Do 20 iterations. Start with an image of random noise, and then again, like let me try to do a different one of these. I'll go back up and I'll grab this one right here. So there's 128 in mixed 3A pre-ReLU. So go back down, and let's do something like 120. So if I run this now, this will take a little while. Just doing 20 iterations, so it's not too bad. So now this is, okay. So this is what we get at channel 120. So let me actually open that there. Try to change this to like 105. Completely different, right? Isn't that neat? And notice that now these actually have different, they have different kind of color properties, because inherently each of these features, they look for different colors as well, but you wouldn't really get that if you don't use this Laplacian normalization process. You'll end up getting just like super high colors all the time. The Laplacian normalization actually gives them a little bit more color definition and color contrast from each other. So that's kind of like, for our purposes, that's what you can think of it as doing. It's not really. It's more of how the canvas is processed as we're adding the gradient to it. Yeah. So
there is one optimal image.
well, there may be one. There is technically one optimal image. There should be one image which is optimal, but it's nearly impossible to find it, because gradient descent cannot really guarantee that we'll ever find the optimal image.
So are these must be better.
You could say they're local optimum. Yeah, they're local optima, right? Yeah. So try to play with these a little bit, and actually it might be useful to kind of copy these into like a text file that you can kind of keep as a reference, so you don't have to keep scrolling. So I'm just gonna like put this into a text file, put that right there, and now I'll go back to the code, which is down here, and like just pick a random one and just see what you can find. And here's the nice thing. So like in the early layers, like I'm gonna pick one of the first ones right here. You'll see that the features, first of all, it's going to be a lot faster, and the reason why it's a lot faster in the early layers is because it only has to propagate through a few layers. It doesn't, because this always has to do a forward pass through the network, and it does it many times. And so if you do it in an early layer, it doesn't have to go through the entire network, so it takes a little bit faster. And you see that the features are very simple. The features are basically edges, right? Because these channels in the early layers are just looking for really simple edges. And they're pretty cool looking, right? So a lot of them are, they remind me of like analog feedback, like video VJ feedback type stuff. So these are the early layers, and they're very abstract. If we move on to like somewhere in the middle, so let's look at like mixed 4A 5X pre-ReLU, and I'll do like, and how many of them are there? There's 48 of them, so let's do 40. Right, so if we look at this one, it'll be somewhat more complex patterns. It takes longer though. Notice that it takes longer. Okay, and these patterns are somewhat more complex, right? Choose a different neuron. right? Pretty neat, right? And then if you end up going to like one of the really late layers, like, okay, now I'm gonna pick down this one, mixed 5B. There's 48 there. So if I switch to that and do, 11, let's say, now it's gonna take the longest amount of time because it has to propagate through the entire network, and the features are going to be the most complex. And you're just gonna start to see just a mishmash of what looks like real objects. Like I see some eyes and stuff in here, there's a lot more sort of. I actually don't really like the later layers because they start to look like a mishmash of stuff. There's not as much contrast between them. So the middle layers I find have a nice happy compromise of like distinction from each other, but also complexity. See that they start to look kind of the same. But they're much more complex, right? So you can see that they look almost like animals here. Now again, you can modify some of these numbers, so I'll just tell you briefly, I'll remind you what each of these numbers are. So 200, 200, that's the initial size of the canvas. So this image is actually bigger than that, and the reason is because it gets resized for 3 octaves by a ratio of 1.3. So at the first octave, it's 300 by 300, or 200 by 200. Then it gets resized by 1.3, and then it gets resized by 1.3 again. So the next image has been resized twice, and that's what we get back. So if you make the ratio bigger, let's make this 1.9 now. Now the output will be bigger as well, because now we're visualizing, or we're doing this process at a bigger ratio. The resizing process at a bigger ratio, which means it'll also take longer. So rule of thumb, more pixels takes longer. And you can see that it's taking much longer, but the image that it'll create will be much bigger. Right? So you can make these gigantic if you want, right? So let's just do like an HD thing, right? So if you want to do HD, maybe we'll do 4 octaves instead of 3, and we want to get up to let's say we want to get up to 1600, right? Or roughly about that, right? So if you want to do 1600, you could do that, that's okay, a little bit bigger. So that's about 1400. Maybe if we make the initial size 250, 240, let's say. Okay, so let's make the height 200 and the width 240, and do 4 octaves, 1.9, 25 iterations. So this is going to make a really big image, and we can I'll change the channel to 4. And you can, again, feel free to just modify these numbers however you wish. This will now take the longest because it's doing 4 octaves, it's doing more iterations, it's going to have more pixels to do this on. So you see it slows down considerably for each octave. So we might be waiting here for 1 to 2 minutes to make this. But when it's ready, it'll be a big HD image. Do you have a question? Oh, so sorry, what? It's just the names of the inception graph. I don't know. I guess okay. So pre-ReLU means they're before the. We haven't talked about these mostly. It's it's before the activation function. If you want to know, it's right after the dot product's taken and before the activation. And ReLU is a type of activation function. But we haven't really talked about that, so it doesn't make sense. So you see the last one's taking its time. Anyway, while this is doing its thing, I'm going to just tell you about. So first of all, this function RenderLaplaceNorm. You'll see it might have a different name, but this is basically the function that you'll find in the TensorFlow Deepdream tutorial. So you can actually find this in the official TensorFlow repository under models and examples. So at that point, from here, I'm going to add some stuff to it, basically stuff that I've added to it to get a little bit more dynamic behavior, basically, which we're going to play with a little bit. And it's the stuff that I added basically so that you so that I could make the video that I showed you at the end of yesterday. So by the point that we get to the end of the notebook, you'll have just about everything that I needed to make that video, more or less. So you could recreate it with completely differently, if you wish to. Because you can see how much power we have. Like, all we have to do is change a single number and the thing looks completely different, right? Okay, let's check this out. Here's our, right, so that looks pretty neat, right? So people getting some good results? Anyone's getting some graphics that they like? We're gonna start to, now here's the thing, like, and this is why I made the additions to it that I made. The nice thing about this is that it's, well, all right, so the nice thing is that it looks pretty crazy, right? And there's a lot of variety, but it feels like overpowering a little bit, right? Like how do you really put in your own artistic touch when the thing seems like it does everything for you? So the next few cells are going to reintroduce some certain aspects of control, which will give us a few ways of getting some more like specific controls that we don't have. And so let me tell you about them, right? So in this next cell called LaplaceNormalization, there's basically two innovations made, or one innovation in two parts. So here's the idea. So far in the functions that we've seen, what happens is that we basically define a single objective, right, which is to maximize one neuron of one layer in the network and maximize the activation of that, maximize its activation at every point in the image, right? So what we're now going to do is we're going to say, okay, let's have multiple objectives that we can combine in different parts of the image, in different regions. So like, let's say, so let me see if actually the next example is, okay, yeah, so check out this example. Before you execute it, just like look at the example. So this image looks like it has two of the patterns, right? It has one at the top and one at the bottom. And it's actually just one image, but it has two different neurons that have been visualized. And it's been visualized just one rectangle on top of the other. And in the next cell, okay, not the kitty there, but in the next cell right here, oh, this actually, that doesn't look right. I'll have to fix that, but okay, let's just look at this example. What I've done here is I've defined, I've created this, we can pass in now two objectives, which is to say two channels that we want to visualize from two different layers if we want, and a mask which will sort of gate the gradient. So let me just remind you what happens here. In here, in the image, or sorry, in the function, at every iteration, we calculate the gradient, and the gradient is the difference in all of the pixels. And then we add the gradient to the image. So what if we take that process, but we actually apply a mask to the gradient? So in other words, like, we multiply the gradient by 0 somewhere so that we don't actually add it to the image. So we say, in this part of the image, we actually will not add the gradient of this particular objective, this particular neuron objective. We don't actually add it to this region of the network, to this region of the image, but we do add it to this region of the image. And the mask in this case is like, for one of the neurons, right, for this neuron that looks like this pattern, the mask basically is just a structure that's the size of the image, and it has ones all over here, and it has zeros all over here. So when the gradient gets calculated, all of the gradient gets multiplied by the mask, point-wise, element-wise. And so here, it gets canceled out to 0, and here it's just gets passed through, multiplied by 1. And then we have a second objective, which is this neuron that looks like sort of mouths or noses or something. And we do the exact opposite. We have a mask which is 1 at the bottom, and 0 at the top. And so here what's happened is we've passed in two objectives, these two channels that we've elected to visualize, and we pass in a mask, which is the size of the image. So you see that the mask is initialized as a bunch of zeros, and its dimensions is h by w. It's the size of the image, so height by width, and it has a depth of 2. So this number 2 has to match this number of objectives. So there's two objectives and there's two channels to this mask. One channel for the first one. The first channel is for the first objective. Second channel is for the second objective. So that gets sent to LaplaceNormalization along with this list of objectives, which is to say the channels that we want to visualize. So this gets passed in along with the simple image and the mask. So basically, like, okay, again, let's try to change this. So here, we'll leave, I'm going to just select a different neuron, so let's use 5 and 8. Okay, so we have these two objectives, this one right here, which is that layer, and then channel 5, and then this layer, channel 8. And then this mask, let's do it differently, right? Now, okay, I just want to take a quick aside. So we haven't done any Python coding here. So for those of you who have never coded in Python, this like NP stuff, Numpy, is not going to make sense to you. How many people here have used Python before? Okay, like maybe a third of you or so. Those of you who have used Python, how many of you have used Numpy? Okay, like less. It looks like maybe a quarter of you have used Numpy. So like roughly a quarter of you will know what this means, right? You can see this and you basically understand what's happening. We're slicing the mask, the NumPy array. We're taking the first 150 rows and all of the columns and the first depth slice, like the first channel. And we're saying all of that is equal to 1. So it starts as all zeros, and then we say the first 150 rows of the first channel are equal to 1. And in the second channel, channel 1 here, the rows from 150 to 299, those are now equal to 1. So basically you have the first channel is all is 1's at the top, 0 at the bottom, and then the second channel is the other way around, 0 at the top, 1 at the bottom. Does that make sense roughly? I know it's probably, for those of you who haven't done Python, it's like a lot to take in, but you can kind of see. So like let me make a quick change to this. How about this? We'll do, instead of rows, we'll do columns. So we'll say that this is going to be equal to, the mask will say all of the rows and then the first 100 columns. So we'll say 0 to 100. So that's equal to 1. And then in mask 2, we'll say, how about we'll actually go from, we'll have them overlap even. We'll say 70 to 2, well, okay, so there's 400, so it goes up to 399. So if I do that, and I run this, oops, of course I forgot to define it, so make sure you run this cell first, and then run this. Okay, cool. So you notice that like the first 80 columns, or sorry, the first 100 columns are visualizing the first channel, which is this one right here. And then from 80 to 400, so they actually overlap. So there's like a column of about 30 cells, which is sort of trying to maximize both at the same time. In fact, we'll see this a little better if we go, let's say from 0 to, let's say almost half, like go more than halfway. Go 0 to 250, and then do 150 to 399. So now they'll overlap for 100 pixels, roughly 100 pixels, yeah. So let's try that again. So in the first 150, we have only we're only visualizing the first channel. In the next 100, where they actually overlap, so you see that kind of elements of both are coming out. And that's kind of the neat thing. So like when you're trying to maximize two neurons at the same time, two neurons activations at the same time, then you're kind of forcing it into this process where it has to try to satisfy both of these objectives. And so you end up getting an image which kind of looks a little bit like both features. And so that's kind of the beauty here. Like we can actually begin to mix and match these by having their masks overlap. So here, and then in the last 150 columns, it's just the second one. So try to messing with these like, okay, so this will be more obvious if I use like one of the early layers. So like I'll do this here, and I'll do mixed 5. Let's do one of the mixed 5. And let's do 15 or something, and then 28. So if I run this, this should show us more contrast because we're mixing a very low layer 1 and a very high layer 1. And it actually ends up being that like the simple one overpowers the less simple one, but you can kind of see a little bit of both kind of coming through. They blend nicely. It's a nice thing. So does that roughly make sense? What do you mean less than? Oh, well, the thing is that ultimately I end up making everything add to 1 or go up to 0 to 1 because you already have this sort of scaling factor, which is the step size. And so by convention we make it 1.0, but it's really more the ratio that makes a difference, because otherwise if you want to get more gradient added on, then you just do more iterations. It's really the ratio that kind of.
In this case, we would have one that you overpower for the other. You wanted to see more of the second.
Yeah, like maybe we could, like, okay, let's say like maybe it'll make more sense to kind of try to reduce this one. So like we'll say up to 150 it's 1.0, and then from 150 to 250 it's like, I don't know, let's try 0.5. Let's see. Yeah, that works. You can see there's a little bit more blend. That's kind of neat, actually. Now here's the thing. Like at this point, I've shown you the core stuff. Like the idea that you have this mask, and the mask controls how these things are blended. So there's all sorts of ways of, like, this is a very simple way of doing a mask, where you just have rectangles, right? Let's try something a little bit more complex, right? So in the next. Oh, actually, and before I do that, I want to show you what happens if you start with a real image. So here, what's going to happen is it does this cell is identical to the previous cell, except instead of making the image be random, the initial image be of random noise, it's actually going to start with an image of a kitty, which it downloads from GitHub. So it's going to load the image here. So it downloads this image, and then it will do this process on top of the image. So you end up starting with this image of a kitty that looks like this, actually. So this is the initial image, and then this is what we've done to it. It's pretty groovy, right? Okay, so now we're going to make a more complicated mask. And so what we're going to do is, there's a function in Numpy called linspace, for like linear space, which gives you a set of numbers that go from like linearly spaced numbers between two endpoints. So like if you look at this right here, it goes, okay, for the first channel, we're going to make all of the this says, okay, for all of the rows, they're going to start out at 0 and descend to 1 and it's going to be a vector of length w. That's the whole length of the whole width of the image. And it starts at 0 at the very left extreme, and then to the right extreme it ends up at 1, and it's linearly spaced, so it's a line. So, it goes from 0, 0.1, 0.2, up to 1. And then on the second channel, it's the exact opposite. It goes from 1 to 0, right? So you basically, they crisscross. So, and then this is actually, we make it really long too. So just to get, so this 256 by 1024, I'm going to change this to, again, like, let's use a different, let's do like mixed 3B and mixed 4D. So how about this right here? And 17 and 29. Okay, so let's run this. And what will happen is it's also going to draw the mask for us, so that will be a little bit more clear. So, like, if you look at the mask, this is the first channel of the mask. It starts at 0 and goes to 1. And then this is the second channel of the mask. Right? And remember, the mask is being multiplied by the gradient. So that's why what happens is that you get this blend between the two channels that we wanted to visualize. Right? You can try a different one if you'd like. Let's try 5921. Oh. If you get an invalid argument error, you are trying to access. There's two, like we went to 59, but there's not that many actually. There's only 32 here, so we got to go down to 31. Let's say. So play around with this, like see, make the sizes different, and if you know a little bit of Numpy, you might even have some ideas of different ways you can mess with this mask. And there's okay, so let's actually so maybe would it be a good idea to maybe have like a few, let's take like 2 to 3 minutes, just play with that cell, like maybe mess with the numbers a little bit, try different channels, see what kind of things you can, see what kind of patterns that you can kind of find. Right? And then there's still a couple more things I'll show you, but we'll get to that in like 1 to 2 minutes. Okay, like maybe I'll try to change this to, let's make it bigger. And what can we do? Like you could, so one thing I think if we wanted to, we could do it the other way around, like maybe if we do this by H and then you do this T to get the transpose. I think this will, I hope that works properly. No. 512, yeah. Give me a thumbs up if you've made an image that you like. Give me a 2 thumbs up if you're overwhelmed. 3 thumbs up if you're overwhelmed. Let me show you a couple more quick tricks, and then we'll end up taking a break, and then the second half of this lecture will be just second half of today will be a lecture about generative models. So we're gonna start to see like more crazy things as we go. So there's two more things that I'm adding to this notebook. One is how to make circular masks. Okay, so now this is just a bunch of, again, like for those of you who have never seen Numpy before, this is like relatively advanced code. For those of you who have seen Numpy before, this is like some optimized Numpy code to make a mask, which is basically like a circle starting from the center. So this will actually make a mask that we can actually visualize the mask. So here, let's do this. I'm going to display mask at 0, 0. So this code will basically make. Oh, well, of course, why is it, right? Hang on a second. This should look like, yeah. So this code basically makes a mask that looks like this. So this is the first channel. So it starts at 0 in the center and becomes 1 out at the ends. And this one, and then the second channel is the other way around. And so this code, if we go back to it, will basically render two objectives. And I want to, again, use one of these early. And so now it's going to blend them together at the center. What do you mean two images separately?
Well, generated an image for each channel separately, and then blended them with some function.
Oh, well, yeah, I mean, that's just your normal blend, right? Like, that's just compositing two images, right?
Yeah, but I'm saying could you get the same blend?
It wouldn't quite, so the reason why this kind of works nicely is because it does this process iteratively. So it calculates the gradient at each step of, like, several dozen times. And that's kind of like, if you do them separately and then combine them later, you're not having this process where it actually has to like converge on features that blend, that kind of satisfy both neurons at the same time. So you see how one of these channels is kind of more at the center and the other one is more on the outside. Right? So this is how you get this kind of circular effect. Now remember I showed you the video yesterday that had like the two faces in the middle. So that was basically taking a source image and then doing some sort of a segmentation of the image and then using each of those segments as masks and then just putting them together. So there was like a hair. There's, instead of being shaped like a circle, it was shaped like someone's hair. And then the other one's shaped like someone's face, and then the other one's shaped like someone's shoulders, and so on. And you can combine more of these, right? So we can have 3 objectives, 4 objectives, as long as there is one channel for each of those channels in the mask here.
But do you try to optimize for all the objectives at the same time? So find one image that satisfies everything, or you have different ones and then you mark up the result?
Well, that's what's happening. Each one gets calculated individually, each objective, but then the thing is that the gradients are added to the image at each step. So it does this thing iteratively, and because it calculates the gradient at each step and then adds it at each step, you're always calculating the gradient on the combined image. So same question. I think it's. Well, they are getting blended. They're getting, so the gradient for each channel is being added at the same time together. They get calculated separately, but the gradient is very small, right? And so you add both of them and then recalculate. And so since you're always calculating on the whole image, you end up getting this process that has to satisfy both. Well, I don't want to confuse everyone. There's a technicality to that where it's like you're technically calculating the gradient for each channel individually, but you still have this, what you end up getting is something that satisfies both like at the same time because of this iteration process where you're adding an infinitesimally small amount of it at each step. Something like that. Yeah, I could do better to.
You don't have enough number of channels, it just becomes
Pretty much, yeah. So the last block of code in this notebook shows the basic idea for making a video, and actually it doesn't make the video here. What it really just does is it makes a bunch of frames, a bunch of images. So how do I make a video, right? Well, let's say I've made one tiny one, right? So here's one little block. What I can do is I can take this image, and here it is, right? We could, let's say, crop it, like, we were to, let's say, crop it slightly. And then we would take that cropped image, and then we would resize it so that it gets back out to the same size as the last one. So like I take this image, I take a crop of it, and then I resize it so that it gets back to this size. And then I use that as the input image to the same exact process for the next frame. So if you do that repeatedly, you end up getting, so like you start with this, and then you do it to the cropped image, and then do it again, and you see that it basically gets this zoom in effect. And as you zoom in, as you bring out smaller and smaller things and make them bigger, it just keeps on calculating, it just keeps on doing the same sort of visualization process on top of the new pixels. And so you get this infinite zoom effect. Right? And you can do this script will do it for some number of cells. So you can run this through again if you wish. And now the thing is, right here, what it's doing is that it's printing the image to the screen, printing these images to the screen. If you wanted to save the frames, you would need to do something a little tricky with Colab, because with Colab, like, you have this ephemeral storage, and they have a guide on how to save things to local storage, which I don't have in this notebook yet. I'll add that at some point. But you can definitely find that if you wish to create video frames. So that's the end of this. I think that's the end of the notebook. Let's see, is there any more slides? Yep, that's it. Oh, it's hello world. So that's the basic idea, right? So this is neural synthesis, as I call it, or Deepdream, and it's like, again, it's kind of interesting to consider that it came out of research that was initially interested in using this technique for visualization purposes, so we understand a little bit about what the network is learning at each channel, but it has evolved into basically an art, like an art form, and there's been lots of work in this area, lots of people doing it, and you can kind of find different iterations of it online. So let's do this. Let's take a quick break. Feel free to just keep playing with this notebook, maybe making changes to it, making some images, and when we come back, I'm going to tell you about generative models. Right? Okay, so let's take a break.